Transaction. So transaction is paramount in OLTP databases, and it is very important in OLAP databases also. So what does transaction do? What does transaction entail? So it gives you the capability in your database that your data is consistent, meaning that let's say you are using database for financial, healthcare, or insurance industries, or any other industries for that matter. If you are doing some real life transaction, let's say financial transaction, your data would be safe and secure. So let's say you are transferring money from one account to another account, which is a database operation behind the scene. Databases would make sure that if the debit happens from one account, the credit would also happen in the other account. So that is an example of transaction. So it makes sure that your data is consistent in your environment. Transaction is backed or implemented by ACID. You might have heard about ACID compliance, that relational databases are ACID compliance. NoSQL databases are not ACID compliance. Not all NoSQL databases, like DynamoDB is ACID compliant, DocumentDB or MongoDB is ACID compliant. So what is this ACID compliance? So what does this ACID mean? First, A means atomicity. What it tells you that if you are doing something in a transaction, either everything will happen or none of them will happen. It's a all or nothing operation. Meaning, let's say you start your transaction here and you do multiple things in your transaction and then you end it. Now, let's say the operations are insert, then followed by update, select, and delete. Let's say something happens, let's say your system goes down during this select statement, right? So your system fails. It can be your application, it can be your database server, it can be any system. So let's say your system fails during the select statement. Now insert and update are done. So insert has happened, update has happened. So while you are running the select statement, your application has failed, or your database has failed, or your server has gone down, whatever, it can be any scenario. Now what will happen in case of atomicity? Because transaction provides the atomic guarantee, it's a all or nothing architecture. So as you can see, all has not happened because delete is still pending. Either it is all or nothing. So the insert and update will go away. The transaction will roll back and it will come to a state where it was before start of the transaction. So this is what atomicity means. So either everything will happen or none will happen. Now let's say the scenario can happen anywhere. When you are running the insert statement, let's say you are inserting multiple rows and it fails. Let's say after inserting 50 rows, it fails. There are still another 30 rows to be inserted. It does not matter. It will roll back. It will go to the state. The insert will be cancelled. It will go to a state as it was before the start of the transaction. Let's say your insert and update is successful and your transaction has failed here. Either the application has failed or the database has failed. Even though your insert and update are successful and this is the transaction, it's an all or nothing architecture, the insert and update would be undone. The database will take you to a place as it was before the start of the transaction. Same is the case here also. It does not matter. So let's say after delete, there's some time. So if you see, there's some time available here before the transaction ends. Now, even though your delete is done, even though all of them are done, and your application is doing some processing here, let's say, or your database server is doing some processing. Now, during that processing, it fails. During the processing, the application fails, even though all of them are done. As you have not ended the transaction, everything will be undone. The delete would be undone, the update would be undone, the insert would be undone, and the database would go back to the state as it was before the start of the transaction. And this is the atomicity or the atomic property of a transaction. Then you have consistency. Consistency says that the data must be consistent before and after the transaction. So which is true because it is implemented using atomicity also. Let's say you start a transaction wherein X has a value of 50 and Y has a value of 150. And you do some modifications. Let's say you do some updates wherein you subtract 75 from y, which is 150, and you add 75 to x. At the end, it should be either x equal to 125 and y equal to 75, or x equal to 50 and y equal to 150. So this state and this state are consistent. So the transaction would ensure that your database is in this state or in this state. So if something goes wrong here, it will roll back here. And if it is successful, if the entire transaction is successful, you can be rest assured that the values of x and y are changed in a consistent way. The next thing is isolation. So let's say you have multiple concurrent transactions. What would happen is that those concurrent transactions will not interfere with each other. Let me give you an example. So let's say you have transaction 1, which is updating the orders table where order ID equal to some value. Then you have another transaction which is updating orders table where our order ID equals to 50. And then you have another transaction which has come in, which is updating the same orders table, but order ID is 24. Now if you see, this order ID is same as this one, but as the transaction has not been completed, this transaction will not happen, it will wait. The isolation is implemented using something called locks, and it is true in Redshift also, but in Redshift the lock is not at record level, which we'll see shortly. And the last one is durability. All the changes that are successful are persisted after a transaction completes. So it will not be lost even if the even if a system failure occurs, and it is handled by the storage system. So if you are storing it in Redshift has local storage for DC2 node types, and for RA3 node types we have Redshift managed storage, which is a combination of local SSD storage and S3. If Redshift application goes down, if the Redshift database server goes down, you can be rest assured that the database changes which were made using the transactions would be there. So this is another guarantee that transaction gives using ACID. So whenever someone says that whether the database is ACID compliant or not, it means whether the database is architected in such a way, or the database system is as such that it supports atomicity, consistency, isolation, and durability. If one of these features are not supported in a database, that database is not ACID compliant. So it has to be all of them. It has to support atomicity using transactions, using begin and end, using all or nothing architecture. It has to support consistency, meaning that data must be consistent before and after the transaction. It has to support isolation, wherein concurrent transactions can run, but they'll not interfere with each other. And finally, it has to be durable, which is most of the cases, right? All the databases are durable except for in-memory databases. In this slide, I talked about logs, that isolation is handled by logs. So let's go a little deeper into how logs are handled. What are logs and isolation levels? So in Redshift, we have something called serializable isolation level. What does it mean? It means that the transactions are executed one after the other. Even though there are concurrent transactions, let's say we have transaction 1, 2, and 3, and if transaction 1 is executing right now, transaction 2 and 3 will wait. So when transaction 1 is complete, then transaction 2 would execute, transaction 3 would wait, and when transaction 2 is complete, then transaction 3 would execute. So transactions are executed one after the other. So this is called serializable isolation. Now you might say that if, let's say, there are a lot of concurrent applications which are trying to update or modify the data in the Redshift database, then it might increase latency because the transactions will have to wait. The answer is true. One more thing you have to remember is that Redshift is not an OLTP database, so there should not be too many writes coming into Redshift. So if there are too many writes or updates, inserts, and deletes are coming into Redshift, then maybe you'll have to take a look at whether you need to move that workload to a OLTP database. And OLTP databases do support other isolation levels also. Now let's see with an animation. So let's say we have this orders table and this transaction is updating this orders table. So what would happen, this transaction T1 would take a log on the orders table. Now if transaction T2 comes and tries to update the same table, it has to wait. That's what serializable isolation is. When T1 is complete, then T2 would be executed. Then logs, what are the various types of logs we have? In Redshift, we have access exclusive log. We can denote it with X. So the access exclusive logs are taken when we run DDL operations like alter table, drop table, or truncate table. And if a table is logged using this mode, using access exclusive log, all other operations are blocked, meaning you can't do anything. Then we have access share log, which is denoted as S. Redshift takes access share log when it runs unload, select, update, or delete operations. Now, this particular log only blocks access exclusive log. It does not block any other sessions that are trying to read or write on the table. So remember, access share log would block access exclusive log, or S log would block X log. Finally, we have share row exclusive log, which is denoted as R. Now, this is typically taken when we run copy, insert, update, or delete operations. And it blocks access exclusive log and other share low exclusive log. So let's look at it with an animation. So again, we have the same orders table. So let's say I'm running some DDL statement on top of it, like alter table, and change the data type of a column. So what it will do, this particular transaction will take an access exclusive log on this orders table, or X log on this orders table. So now let's say there are other transactions. One transaction is coming with access share log, which wants to run some select statement or an update statement. Similarly, let's say another statement comes with share row exclusive log, which wants to run a delete statement or an insert statement. Right, now these two will not be allowed. They'll have to wait. And once the transaction which has taken the access exclusive log is over, then only these two would be allowed. Okay, now let's say there's a transaction which has taken access share log. Let's say it is running some select statement or update statement on multiple rows or delete statement on multiple rows. So now what would happen if another transaction comes with share row exclusive log, which is trying to insert one row or update one row, delete one row. In that case, that transaction will be allowed. Let's say there's another transaction which is trying to update some row, delete some row, etc. That will also be allowed because access share log allows other access share log. But if you want to run an alter statement on this particular table, it will not be allowed. It will be blocked. Then finally, let's say there's a transaction which takes share row exclusive log. So in this case, let's say there are two other transactions. One is running the access exclusive log and another transaction is running share row exclusive log. So what do you think what would happen? Please pause the video and think about it. All right, I hope you have got the answer. Access exclusive log will not be allowed and share row exclusive log will not be allowed as well. So if you see in the share row exclusive log, it blocks access exclusive log and it also blocks other share row exclusive log. Now if a access share log comes, only it will be allowed. So we have gone through the concepts of transaction, the ACID compliance or the ACID semantics, the different types of logs and isolation levels which are supported by Redshift. Now, how do we implement transaction? So when logs are taken, how logs are taken, so on and so forth. Let's say this is the start and this is the end. So how do you start a transaction? There's a command called begin. So using begin, you are telling Redshift that I'm going to start a transaction. Now inside of this begin, let's say you run update statement, delete statement, select statement, insert statement. Then after all these are done, you want to close the transaction. So either you commit, meaning that you want to apply all the changes to the database and make it durable, or you roll back, meaning that you want to undo all the modifications that you have done using these statements: update, delete, insert, and select. So this is how transaction is implemented in Redshift. Now we can check the transactions and logs using these system tables: SVV transactions and PG underscore logs. Please forgive me for bringing up the system tables here abruptly. The reason is that we need to know these system tables, because if you are running some transaction, if you are running some statement, how do you know what log has been taken? So I'll show you that in the demo, and we'll be using these system tables to find out what logs have been taken by Redshift when we run certain types of SQL statements. Now going forward, I'll be pulling in system tables as and when needed. So these are the two system tables: SVV underscore transactions and PG underscore logs, which can be used to see transaction and logs at a rudimentary level. We'll try to go a little bit deeper also. As usual, let's have some hands-on on transaction.